Okay, let me start by saying a little something to everyone about next week's quiz, just what you need before Thanksgiving. It will probably turn out kind of like this. A question involving straightforward conditional probability. The prototype for this is the original bearded man problem, and there are lots of others in this genre, and I can think up large numbers of them. Something involving random variables, perhaps binomial, perhaps geometric, perhaps negative binomial, but something where you have to work out a few values of a mass function and an expectation. Something involving series. Now, I got burned by a problem in this genre last year, but I'm going to try again. You might, for example, end up having to say, but this is the series that sums to the exponential function, in which case it would almost certainly involve the Poisson distribution, or it could be conceivably something related to the tail sum theorem. Last year, on both versions of the quiz, this was the problem that gave most people the hardest time. And I think I've gone a bit out on the limb by saying this course requires no calculus, but we're going to do infinite series. Nonetheless, one of my goals is to get people a little bit comfortable in dealing with infinity. And then number 4, I can only characterize as off the wall. I don't know if you think that Monty Hall is off the wall, but there are various generalizations of the Monty Hall problem. There are various problems involving people who tell truth some of the time and tell lies some of the time, like the Solomon problem and the Eddington's controversy problem. And that will be plenty enough to keep you entertained for an hour. My plan for next week is, you may have noticed there's no homework assignment due next Tuesday. There are a couple of problems from the book that are difficult enough that I want to work others just like them next week. And I'm also happy, if time permits, to work through a couple of other homework problems. I know there's that one involving you add 1 to the first term, you add 2 to the second term, that Jerry managed to work out, though I finally, this was the one from the book where it said there were no repeated values from way back when.
Oh.
Is it lottery?
Oh, yeah, okay. I think I know what you mean.
This was the one where the part that I hadn't fully understood was that when it said there were no 2 consecutive values, it meant you couldn't have a 4 somewhere and then a 5 much farther along. So anyway, if people will email me about homework problems they would like to see me explain, rather than starting the whole new topic of random sequences and Gambler's Ruin and that sort of stuff, I would like to devote the second half of next week's lecture to homework problems and closely related things and sort of wrap up this part of the course before we go on to the last topic. Yeah, Jerry?
A 2-part question. Will next week's lecture be online eventually?
Of course.
And when?
A day or 2 after it's given.
Because the holiday is coming. That's why I won't be here.
Oh! I'm assuming that the folks in charge would be unwilling to sit down and eat turkey before they have the lectures online. Is that a reasonable assumption? That's the answer.
Shall we make that the subject of a probability distribution?
You mean the random variable is the
only
number
thing
of days
I'm
after next Tuesday?
I'm getting back on Saturday, and I would
Certainly,
like to look at what you've done before
I would
come
be
back here.
scandalized, and I'm saying this on the record, if the lecture was not put up there quickly enough for people to use it over the weekend. And it really looks as though they're getting these things out typically by early afternoon on Wednesday. So Thanksgiving shouldn't pose a problem. Questions about the quiz? Okay, so tonight I'm doing a final collection of stuff involving expectation. The major new idea will be conditional expectation, which is a little bit subtle but a very useful computational device. But what I want to start out with is topic number 3, which is infinite expectation. And I apologize. I got an email from Patrick about the problem on the homework with the 19s and the 20s in it. And I had missed the subtlety that created the problem, which is basically whether it's less than 10 to the nth or less than or equal to 10 to the nth.
Yeah, it has to do with the cases where you end up picking a number like 10 or 100 or 1,000.
That's right. And so that messes up the number of digits in the answer. And I think I had misread the problem as what the author had intended to write and then solved it. And I thought, this works fine. This is a great problem. So I can address that next week also. But that was one case that gave rise to infinite expectation. Here is another example. And I should say, you recall that last time I finished up with a problem involving undefined expectation, a case where a random variable assumed both positive and negative values, and the expectation is undefined. Having the expectation be infinite is a much more reasonable situation than having the expectation be undefined. All the time you run across random variables whose expectation is genuinely infinite, and you have to deal with them mathematically, and you also have to deal with them in real-world examples. This one goes by the name of the St. Petersburg paradox, though what the paradox is, I cannot see. I guess the paradox is the expectation is infinite, but no reasonable person, Russian or otherwise, would pay an infinite amount to play this game. So here's how it works. You flip a fair coin over and over and over again, and sooner or later it'll come up heads. So the random variable t is the number of flips until a head appears. And as soon as a head appears, you get your payoff, and your payoff is 2 somethings, probably 2 rubles, to the power of the value of the random variable, capital T. So we can make a little table here. The head might come up the first try, the second try, the third try, the fourth try, and so on. And it's perfectly easy to work out the probability that the random variable, capital T, has the value little t. The probability of getting ahead on your first flip is 1/2. If you didn't get ahead on your first flip, you have 1 chance in 2 of getting it on the second flip. So 1/4, 1/8, 1/16. And what series could more clearly sum to 1 than that very nice geometric series? And then there's the payoff. This is another random variable. I'll call it x. And this is a pretty good game because the payoff is 2 raised to the random variable t, which means that the payoff is 2 rubles, 4 rubles, 8 rubles, 16 rubles, and so on, respectively. So if this coin keeps coming up tails time after time after time, you know you're going to win a whole lot of money. To be precise, the expectation of the random variable capital X, and now I'm going to use the law of the unconscious statistician, is the sum from t equals 1 to infinity of the value of the function of t, that's 2 raised to the t power, multiplied by the probability that capital T equals little t, which is 1 over 2 to the little t. So that's the sum from t equals 1 to infinity of 2 to the t times 1 over 2 to the t, which is 1 plus 1 plus 1 plus 1 plus 1 dot, dot, dot. In other words, you got a 50% chance of winning 2 rubles, you've got a 25% chance of winning 4 rubles, 12.5% chance of winning 8 rubles, and so on, and your expectation is infinite. No doubt about this. This isn't a series that subtly fails to converge. This diverges blatantly. And I think what made this problem interesting when the Bernoullis posed it in the 18th century is that no reasonable person would pay an arbitrarily large amount to play this game. So it's fine to say your expectation is infinite, but if someone said, hey, Paul, would you like to put up $1 million for one play of this game? I would say no. And I think the reason is the infinity is very much caught up in the small probability of winning 4 billion rubles or something like that. And most people would say 4 billion rubles isn't worth twice as much to me as a mere 2 billion rubles. That's a matter of my utility function. And an economist looking at this would say, what someone calculates in deciding whether or not they want to play this game or how much they're willing to pay to play it is the expectation of their utility function, which, given tax rates and the difficulty of spending vast amounts of money, is not a linear function of the payoff. So this could probably be reformulated in reasonable terms by an economist. And another interesting thought about this is, suppose you had the entire population of St. Petersburg playing this game, a consortium. Then it becomes a much better deal, because if you've got a couple of million people playing, some of them are going to cash in on the big payoffs, and then if you split everything up, it becomes a reasonable deal for everyone. And what's happening there is, if you get 1 part in M of the total amount attained by M people playing this game, your expectation is still the same, but your variance is a whole lot less. And the big problem with this is, yes, the expectation is infinite, but the variance is also so large that you don't have a good chance of cashing in for much. I should say, when I was cruising the Baltic with my wife last summer, we went on a wonderful tour of St. Petersburg, and I asked the guide, where's the building where Euler and other famous mathematicians used to work when they were here in St. Petersburg, which was quite a center of mathematics? And she pointed across the Neva River and said, there it is, that's the Academy of Sciences, the Akademia Nauk, and this is a fairly famous place in the history of mathematics. Okay, so that's St. Petersburg. Now I want to move on to the Royal Oak Lottery. This, I assume from the way Sturzaker describes it, actually happened. And I think it's a wonderful idea of gulling the public. I have simplified the numbers so that the calculation is a bit easier to do. But here's the way the Royal Oak Lottery worked. The lottery master put up a lottery that no sane person would play unless motivated by charity. I think you put up money, you had 1 chance in 32 of winning, and you got 28 times your bet back if you won. So this is clearly a chump's game. But in order to show the public that this was a reasonable bet, the person who was running the lottery said, look, just to show you how much I trust this game, I'll lay even money that I will get paid off within 22 attempts. And if I'm willing to bet that I'll get paid off within 22 attempts, and you get paid 28 times back your bet, this is a really good deal for you. And I assume that people must have fallen for this, or it wouldn't have gone down in history. So here's my much simpler version. So this is topic number 4 now, the Royal Oak Lottery. And the trick to one of these involves finding a power of n minus 1 over n that is just a teeny bit less than 1/2. The one that was actually used was spectacularly close to 1/2, but mine is fairly close. What I've said is you roll a die, and if you get a 6, you win $5. Otherwise, you lose $1. Sorry, I've said this wrong. I've got to say this is $4 net. That is, you pay $1 to play the game, no matter what, and if you roll a 6, you get $5 back for a net gain of $4. Otherwise, you lose your $1. So this is clearly a lousy game to play. For one play, if we introduce a random variable, let's call it capital Y, to mean your net payoff is $4 with a probability of 1/6 and minus $1 with a probability of 5/6. So E of Y, the expectation, is 4/6 minus 5/6 or minus 1/6. If you got back $6 for your $1 bet when you rolled a 6, this would be a fair game. So the question is, how can you convince people that this is a reasonable game to play? And what the inventor of this lottery did was to exploit the fact that most folks don't understand the difference between the median and the mean. So let's think about playing over and over again. I'm going to need a lot of space. I'm going to erase what I've written so far. So let's imagine that you play until you win. And when you play until you win, capital X is a random variable. It's the number of tries until you win. Okay, we're rolling a die. Every time you roll the die, you've got 1 chance in 6 of winning, 5 chances in 6 of losing. Katie?
Question that came up in section today. You wrote there until you win. Does that include your winning try?
Yes, until includes the winning try, before does not. On exams, I will try to be even more explicit than that, but it's the preposition that makes the difference. Until includes the winning case, and before does not. Okay. So what kind of distribution does this random variable have?
Geometric.
Yeah, it's a geometric distribution. And we can actually make a sort of bar graph to represent this. The chance of winning on your first try is 1/6. The chance of winning on your second try is 5/6 times 1/6. The chance of winning on your third try is 5/6 squared times 1/6. The chance of winning on your fourth try is 5/6 cubed times 1/6, and so on. Now, these numbers have the following interesting feature. It's very easy. I'll put some more bars in here because I want to talk about them. I'm still going to leave myself room to calculate the probability that the number of tries before you win is greater than 4. What's the probability that you roll a die 4 times without getting a 6?
5/6 to the 4th.
5/6 to the 4th. And when I work this out, this is 0.482 and change. I actually used Mathematica for this. I didn't use a calculator. So that means the person in charge of the lottery can say, look, if you're skeptical about this lottery, I'll bet on my own lottery. I will bet $1. And if I roll a 6 within 4 turns, I'll get double my money back. If I don't get a 6 within 4 turns, the house gets to keep my money. And I'm sure if I'm asked to do this over and over again, I will just get richer and richer, right? Because the probability that it will take more than 4 rolls to get a 6 is slightly less than 50%. And what that means is that the median for this probability distribution is here. That is, more than 50% is here, less than 50% is here. I don't want to get into much fuss about whether we should put the median there or there, but you get the general idea. With a probability of more than 50%, a 6 will come up within the first 4 rolls. But now, you play this game over and over again, and you have to keep paying every roll until you finally win. What's the expected number of rolls until you win? This is a geometric distribution. 6, yeah. So the expectation of the random variable x is 6. So if you resolve to play this game until you win, you will win $5 when you win. You will pay out an expected $6, and therefore the expected winnings are the $5 you win minus the expected $6 for the 6 tries it takes for you to get your 6. And if you resolve to play until you win, your expectation for that is -1, which is quite reasonable. We've already agreed that your expectation on any individual play is -1/6. Since it takes you an expected 6 turns to win, it's not surprising you expect to lose $1. If you look in the textbook, you will see the actual numbers. In the actual lottery, instead of having 1 chance in 6, you had 1 chance in 32 of winning. I assume they put 32 balls in an urn or something like that, and 1 was the lucky ball. And instead of winning $5, you win 28, not 5. So, your expectation really isn't very good on this. You get 7/8 of your bet back. And the clever thing about this is that the probability that x is greater than 22 is equal to 0.497 and change. So these numbers must have been devised in such a way that this, I bet you that I will win within 22 tries, was as close to 0.5 as someone could make it. On the homework, I have invented yet another case of this, where we don't come quite as close to 1/2 as this, but we come substantially closer to 1/2 than this does. But the basic message about this is you've got to watch out. There's a difference between the median and the mean, and someone who played this game would probably notice this. Because what happens is, suppose you win. If you win, you're not going to win that many plays before turn number 4, right? So you'll pay $1, $2, $3, but never substantially less than $4. Whereas every once in a while when you lose, it will take you 10 or 15 or 20 times to roll that 6. And it's this long tail out here that makes the expectation so much greater than the median. And if you're going to play something over and over and over again, it's the expectation rather than the median that should matter for you. Okay, next problem is another dog bite problem. Some canine league is probably going to come after me because the only context in which I talk about dogs in this course is either they bark a lot or they bite a lot. But this is a nice example from the book under the topic Poisson as limit, which is based on actual statistics of dog bites somewhere in England, and is a nice example of making a simple probability model to answer a question where at first glance you'd say there's not nearly enough data to answer that. So the available data is somewhere in England, I forgot where, there were 1,103 postmen and 215 dog bites. Now, we can make a nice random variable out of this. The random variable x is the number of bites sustained by a specific postman. And an interesting question to ask is, what's the probability that a specific postman will be bitten precisely twice in 1 year, given that there are 1,103 postmen and 215 reported instances of dog bites? And an initial reaction is to say, there's just not enough information to make a reasonable answer to that question. But if we make a model for the behavior of dogs and postmen, we can do it. First thing I want to point out is the expectation of this random variable is perfectly easy to calculate. The expected number of dog bites for a postman is 215, 11 1/3. Now, in order to make a model of this, we have to say each of these 215 dogs picks a postman independently at random and decides to bite him. So every time a dog decides to bite, he goes after one of the 1,103 postmen in the neighborhood and picks one at random. My wife delivered telephone books briefly about 20 years ago, and her view is that this is not a good model at all. There was one specific house where, as far as she could tell, the dog bit everyone who came up the walk. And the postman at that dog was not biting at random. He was very much sticking to home and biting whoever came up. So this model may or may not be good. And in the book, they have actual data on the probability that this random variable equals 2, and it doesn't agree precisely with this model. But we'll make this model. So we're going to assume that a dog bites any postman postal service worker with P equals 1 over 1103. Okay, now we can solve the problem because it's given by a binomial distribution, right? You're a postman. There are 215 dogs out there. Each of them is deciding to bite one postman or another. And the question is, what's the probability that, let's say, 2 of them decide to bite you, or K of them decide to bite you? So the probability the number of dogs bites you get is K, is easy to work out. With these specific numbers, it's 215 choose K, the number of ways of choosing the K bites that you get out of the 215, times the probability that that bite is aimed at you, times the probability that all the other bites are aimed at one of your coworkers. So does everyone see this? This is the exact solution to the problem, only raising 1102 1103rds to a rather large power. Well, it's something that's perfectly possible on a calculator. Doesn't give you much insight into what's going on. So now I'm going to approximate this. I'm going to approximate this. Let me first make it generic. So let's say this is n choose k times p to the k times 1 minus p to the n minus k. And the really crucial number here is the ratio of dog bites to postmen, right? If you had 10 times as many dog bites and 10 times as many postmen, it would still be essentially the same problem. So what I'm going to do is to define very suggestively a quantity called lambda, which is the number of postmen multiplied by it's the number of dog bites divided by the number of postmen. So this is the number of dog bites multiplied by the probability that a bite lands on one specific postman. So in this particular case, that's our number, 215 divided by 1103. And it is, incidentally, the expectation of the random variable x. Okay, now let's write out what this equals. The probability that this random variable capital X has the value k is this binomial coefficient, and I'm going to write it as n times n minus 1 times n minus 2, so on down to n minus k plus 1. And I still have my k factorial in the denominator. Since I set lambda equal to np, p can be replaced by lambda over n. That's fine. I will write my lambda to the k here, and I've got k powers of n. That I'm going to put there. Okay, I've now dealt with this, I've dealt with that, and I've got 1 minus p to the n minus k. I'm going to split that off a little bit. I've got 1 minus p to the minus k. And then I've got 1 minus, I'll replace this right now by lambda over n. 1 minus lambda over n, which is p to the minus k, and 1 minus lambda over n to the n. Now, because it won't fit on the next line, I'm going to take the limit as n approaches infinity. That is, I'm going to say this analysis will be more appropriate for 215,000 dog bites out of 1,103,000 postmen and so on. But it's the ratio of bytes per postman that I'm holding constant. Okay, what have we got here? K is some fixed number. It's 2. It's 10. It's finite. It doesn't increase as n increases. What does each of these factors approach in the limit as n approaches infinity? N minus small change over n as n approaches infinity approaches the limit of 1, right? And if we had more and more factors to multiply together and they all approached 1, we'd have a problem. But we have a fixed number of factors, just k of them. They all approach 1, and therefore this whole mess up to here approaches a limit of 1. Everyone comfortable with that? We've still got our lambda k, lambda to the k over k factorial. Okay, we've got 1 minus a teeny number raised to the minus k power. As n approaches infinity, this thing becomes closer and closer to 1. If you take something that's close to 1 and raise it to some finite negative power, what's the limit as n approaches infinity? 1 again. Now this is going to tax your memory. What's the limit of 1 minus lambda over n to the nth as n approaches infinity? E to the minus lambda. So the probability that x approaches k, probability that x is equal to k is what? Let's collect the factors we've still got. We've got e to the minus lambda times lambda raised to the k power over k factorial, which is the mass function for the Poisson distribution. And that's why the Poisson distribution is so important. The Poisson distribution is the limit of the binomial distribution where you have a very small probability that something will happen, but you have a whole lot of trials to make up for it. And there are all sorts of classic examples of things that are well modeled by Poisson distributions. For example, there are lots of light bulbs here at Harvard. And, on any given day, any given light bulb will burn out with a small probability. And it's easy to calculate the expected number of light bulbs that will burn out every day at Harvard. It's the number of light bulbs times the probability that an individual bulb burns out. And then this analysis applies almost perfectly because the bulbs burn out independently of one another. So by using the Poisson distribution, you can calculate quite accurately the probability that some specific number of light bulbs burns out. When I first introduced the Poisson distribution, I pulled it out of a hat, and it looked like something whose main interest was in the fact that I could use the infinite series that defined the exponential function. But this example really explains why the Poisson distribution is so important in real life. Anytime you have a situation where you have a very large number of independent events, each of which has a small probability of happening, and you know the probability times the number of events. That is, you basically know the number of dog bites per postman. A Poisson model is a pretty good one to use.
Can you just repeat that again? A very large number of independent
You have a very large number of independent events, like lots and lots of postmen who might get bitten. And you have a very small probability.
What would you define as small probability? Just
off the top of my head, I would say a probability of less than 1/100th, and I'd use the Poisson approximation.
less than 1%.
Yeah. And clearly, if you ask, what's the probability that a postman is bitten 216 times? This gives you a number that's not 0. It's very small, but it's not 0. Whereas there's no way, if there are only 215 dog bites in the town, that an individual postman could receive 216 bites. So you want to be sure that the number of bites you're talking about I'm thinking in terms of a value of k that's more like 2, is very small compared with this. And you can always solve the problem exactly by using the binomial distribution. The nice thing about using the Poisson distribution is you can, when you get your PHP programs up and running, make a nice histogram showing the mass function for this. And it's quite easy to visualize what's going on, whereas, although this is a perfectly reasonable function to write down, understanding how it behaves as a function of k is a little bit difficult. Okay. Other questions about this? Okay, now I want to talk about conditional, well, the title is Conditional Random Var. That's because my wife discovered that conditional random variable has more than 26 characters in it. So I chopped off the end and called it just a var. This is a topic that you may find a bit annoying and say, why on earth do we have to fuss about this? We understand the whole theory anyway. But I'll show you a couple of examples where the only realistic way to approach a random variable is in terms of a couple of these conditional random variables. So this is number 6. Conditional random var. You see, this just stops writing when you hit 26 characters. Okay. So here's a very simple example. You roll a single die, and it's conditioned on the roll being odd. So here's the deal. I'll roll a die. If it comes up even, we won't even look at it. We'll only pay attention to it if it comes up odd. What's the expected number of spots on the die under those circumstances?
3.
3, right? We got a probability of 1/3 of getting 1, 3, or 5. So we can say we have a conditional random variable, and while in talking about random variables in general, I correctly said these have nothing to do with probability. Once we're talking about conditional random variables, probabilities do come into play. So we can be a little more precise about this. We can say we have an event B, which is that the roll is odd. We have a random variable X, which is the roll on the die. And now we can ask, what is X conditioned on B? And you've got to look out for this rather strange notation. This is a random variable. This is an event. So previously, when we've talked about two things with a bar in between them, they both in events. This is a random variable conditioned on an event. If you want to be really fussy about this, you write down the mass function like this. The mass function for X conditioned on B is a function, well, as far as I'm concerned, it's really a function of little x, but it's conventional to put this bar capital B, mainly because people are usually lazy and leave this out. So this is sort of overkill notation for indicating the value of this random variable. And here's what this means. This means precisely the probability that the random variable capital X achieves the value little x conditioned on the event B occurring. And now we're back to notation that we all understand, because this is a straightforward conditional probability. This is an event, that's an event, and we can write this out in terms of the definition. This is the probability of the event X equals X, capital X equals little x, intersect the event B divided by the probability of B. And I think you all did this correctly in your head. You said the probability that X will equal 1, 3, or 5 is equal, the probability, and equal to 1/6. The probability that the event B, an odd roll, will occur is 1/2, and therefore for each of the odd values of X that can occur, 1, 3, or 5, the probability of this conditional random variable is 1/3. Now, we can also talk about the expectation of this, which you figured out. The expectation is calculated in the usual way. The expectation of this random variable capital X given B is equal to the sum over all the values that it can achieve of little x times the mass function for X given B, which is basically 1 times a third plus 3 times a third plus 5 times a third for a total of 3. And so we've already agreed that the expectation of a die roll given that it's odd is 3. What's the expectation of a die roll given that it's even?
0.
Robert? I just didn't. 4, yeah. And a useful check is that the die roll will come up odd half the time. It will come up even half the time. And when you combine those, you get 3.5, which you know is the expectation of a roll on an ordinary die. So this is a specific example of a very general and useful computational technique. You can calculate the expectation of a random variable by splitting your sample space up into a partition of different events. For each of those events, you can calculate the conditional expectation, and then you weight them by their probabilities, and you have an alternative way of calculating expectation. I'm now going to prove that this gives you the right answer, and in the second half of the lecture, I will show you some problems that are pretty much intractable if you use the standard definition of expectation, simply because you can't work out the mass function for the random variable, but that are very easy if you split things up into cases. And we all do this all the time. We say, well, yeah, my expectation for the next year was, well, if I actually get that fancy job I'm looking for, I'm expecting I'll make about $55,000. If our house burns down and we have to replace it, we'll probably be minus $20,000 for the year. And if I'm laid off and just collect unemployment, I'll probably get about $15,000. And then you estimate the probability for those cases, multiply each probability by its expectation, and add it all up. So this style of working out conditional expectations is something that comes quite naturally to people. Okay, in spite of the fact that it comes naturally, I'm going to prove it. So this is now topic number 7. Conditional expectation. And the basic idea is we'll partition the sample space. We'll write the universal event as equal to B1 union B2 up through Bn. And these are all disjoint. So either a die roll is even or it's odd. if you toss 4 coins, you either get fewer than 3 heads or you get at least 3 heads, and so on. And the theorem says simply this. That if under these circumstances you want to calculate the expectation of a random variable x, you can do it like this. You can do it by splitting the sample space into n different events, and then you say, I will sum up the probability of one of these BIs times the expectation of x conditioned on BI. The probability of my getting that super job times my expected income if I get the job. The probability that my house burns down and I have to replace it times my expected profit for the year under those circumstances. The probability that I'm laid off but my house doesn't burn down times my expectation if I'm trying to live on unemployment. So everyone see, intuitively this makes good sense. And it's actually quite easy to work out. All we have to do is write this as a double sum and change the order of summation. So we've got the probability of B sub I, and then we have to multiply this by the expectation of x given B sub I, and it might be worth no, I'll do it like this. Okay. So as my first step, I'll write an x there, and then we have to multiply x by the probability that x equals little x conditioned on B sub I. Everyone comfortable with this so far? That's just the definition of expectation. Now, when you multiply the probability of B sub I times the probability of something conditioned on B sub I, what does a conditional probability times a probability like this multiply out to? The probability of the intersection of the two events. So strictly as a matter of definition, I can multiply this by that and get the probability of x equals little x intersect B sub I. Now this is a rather complicated way to do the calculation. It's saying do the calculation separately for each of the events B sub I and then add up all the expectations. But let's look at what we're actually doing. We're saying we take case 1, and x might equal 0, 1, 2, 3, or 4, but we go up this column to get the expectation of the random variable capital X in the first case, B sub 1. And then we do the same thing for 2 and for 3 and so on. So what this is saying is first for each value of I, you sum up over x in what should be a nice neat lattice. And then having computed this sum for each value of I, you add them all up. What's another way of summing over this rectangular array of points? Instead of first summing over the columns, we could first sum over the rows, couldn't we? So another way of doing this is we first sum over x, and we second sum over I. And since little x doesn't depend on I at all, we can bring that over here. The other thing we're summing is the probability of the event capital X equals little x intersect B sub I. And if you intersect some event with a complete partition of the event space and then add up the results, you get something very simple. What's that? That's just the probability that capital X equals little x. So that's the expectation of the random variable capital X. That completes the proof, and it's really almost trivial. It's saying this formula is just telling you that under these circumstances, you can either sum these things up and then combine the results if you find that convenient, or you can use the general definition of expectation, first sum over the specific cases to get the probability of each value of x, and then use the usual formula for expectation. This is so trivial, it's hard to believe it's going to be useful. But after we take our little break, I will work a number of examples that will show you, first, that this leads to the correct answer, and second, that it lets you solve certain problems without trying to write down in some infinite series. And our general technique for most of the rest of the course will be to solve problems by using this idea of conditional expectation or conditional probability to turn problems that look as though they involve infinities into simple equations that we can solve rather than trying to sum series. Okay, let's take a break for a few minutes. Is runs of heads and tails. This is a very nice example taken pretty much straight from the book. And here's the idea. We toss a coin, and this is only really interesting if it's an unfair coin. If the coin comes up heads with probability 1/2, nothing interesting happens. So we'll say the probability of getting a head, which I'll call little p, is in general not going to be equal to 1/2. Now, this is a situation with an infinite sample space. Here is a sample outcome of this experiment. We get 3 heads and then a couple of tails and a head and a few more tails and some more heads, and it just goes on forever. So there are an infinite number of possible individual outcomes. In fact, there are uncountably many individual outcomes, because if you replace h by 1, t by 0, and put a binary point in front of this, this is the expansion of some real number between 0 and 1, and there are uncountably many of those. Nonetheless, we can deal with this without getting anywhere close to infinity, and here are some random variables I want to talk about. R1 is the length of the first run. Either this is going to start with a bunch of heads, at least one, or it's going to start with a bunch of tails, at least one. And an interesting random variable is the number of repeated symbols at the beginning, which could be h's or which could be t's. And similarly, we can talk about R2, which is the length of the second run. And the interesting thing that I'm going to show you is that the expected length of the first run is greater than 2, while the expected length of the second run is precisely 2. So if you get paid off either on the basis of the first run or any odd-numbered run, you're better off than if you're getting paid off on the basis of the second run. Jerry?
The length of a run is the number of consecutive symbols of the same kind.
That's right. So I left a little space here. In this case, R1 is equal to 3 and R2 is equal to 2, right? A random variable is a function from the sample space to the real numbers. This takes this outcome, something in the sample space, and assigns to R1 the value 3, assigns to R2 the value 2. Now, there are also two other random variables that it's worth talking about, and these are a little weird. X is the number of heads before the first tail. What's the value of X in this case? 3. And Y is equal to the number of tails before the first head. Notice, Katie, I'm now saying before instead of until, so we don't count the tail. And what's the value of Y in this specific case? 0. Now, I have to say, can anyone see, first, does everyone see that either X is 0 or Y is 0? And therefore, what's the simple relationship between R1, X, and Y? It took me a while to spot this, but this is actually a shorter solution than the one I'm going to do, which comes from the book. Yeah, R1 is equal to X plus Y. In general, R1 would be equal to the larger of X plus Y, but if you have two numbers and at least one of them is guaranteed to be 0, the larger of the two is equal to their sum, isn't it? If one's positive and the other is 0. Okay, so now I'm going to condition on my first toss. Condition on the first toss. Event H is it's a head, and I apologize for having used capital H's and T's here. Later on, I use H to mean Harvard wins the series, and I carefully use the lowercase h to mean Harvard wins the game. So I'm using H up here in quite a different context from down here. This is an honest-to-goodness event. Okay, now I'm going to use my conditional expectation formula, the one I just proved. The expectation of capital X can be obtained by splitting the sample space up into a partition. And the partition is simply the two events in the partition are the first toss comes up heads and the first toss comes up tails. So this is the probability of getting a head times the expected number of symbols in the first run, given that you started with a head, plus the probability that the first toss is a tail, the complement of a head, times the expectation of X, given that you started out with a tail. Everyone comfortable with that? X is the number of heads before the first tail. And therefore, as Sue has already figured out, this is going to be pretty trivial. Okay? The probability of head is little p. That's what I mean by little p. Yeah, it is. This brand seems to work better, but well, let's try going to green. Okay, so the probability of getting ahead is little p. Now I can say the probability of the number of heads before the first tail, given that I started with a head, is the sum of two terms. I've got my one head in the bank already, and I'm going to keep flipping this coin, and I expect in the future to get the number of heads before the first tail. So I can write this as 1 plus the expectation of x. Everyone comfortable with that? Once I toss a head, I still have in the future the same expected number of heads before the first tail as I had before I ever tossed the coin. If I'm stupid and believe in the so-called law of averages or something like that, then I won't reach this conclusion. But if I'm smart and I know the probability that the coin will come up heads next time is totally independent of the fact that it just came up heads, then I can write down this equation. And, okay, we got Q. And then, so you can tell us what's the expected number of heads before the first tail if the first toss was a tail? It's 0. Okay, now we're talking a geometric distribution here with these heads coming up. And in the past, we've dealt with geometric distributions by summing geometric series or by using the tail sum theorem. This time, we've got a nice equation out of this. And why don't I just go ahead and solve it? I've got expectation of x minus p times the expectation of x is equal to p, right? And therefore, the expectation of x is equal to p divided by 1 minus p, or p over q if you prefer, which is what you already knew about the expectation of the length of the expectation of a geometrically distributed random variable. And notice this is before rather than until. That's why we've got the p in the numerator. And we can say similarly, the expectation of y is going to equal q over p, because when we interchange heads and tails, we interchange the p's and the q's. So this is nothing new, but it's an interesting way of rederiving a familiar result anyway, because I have managed to calculate the expectation of a geometrically distributed random variable without summing an infinite series and without using the tail sum theorem. I've done nothing that involved infinity. Instead, I have simply noticed that once I toss a coin and it comes up heads, the expected number of heads before the first tail comes up is the same as it ever was before, and that fact has got me an equation. Now, how many more lines can you see below this, Anna and Catherine? Should I go back up to the top?
Maybe one line.
Okay, I've got 3 lines of algebra, so I hope you've got this stuff in your notes. Okay, now I'm going to condition on the first toss. And the random variable that I'm really interested in is R1. So I can say the expectation of R1 is equal to the probability that the first toss is ahead times the expectation of R1, given that the first toss is ahead, plus the probability that the first toss is not ahead times the expectation of R1 given that the first toss is not a head. And I hope this bizarre looking formula is now beginning to make sense to you. You say, when we split up this problem, we want to split it up to two cases. Either the first run starts with a head or it starts with a tail. Let's analyze those two cases and then average them together. That's all we're really doing. Okay. If the first toss is a head, what other random variable is exactly the same as R1?
X.
X, right? Because if we start by tossing a head, what we need to know is how many heads are we going to get before the first tail. On the other hand, if we start by tossing a tail, we've got the expectation of y and yeah, this is right. Okay. Now, there's a difference between the expectation of x given h and the expectation of x. Let's think about the two random variables x and x given h. What's the probability that is the probability that the random variable x is 0 necessarily non-zero, or might it be 0? What's the smallest value that can be assumed by the random variable x given h? 1, right?
Given H, or
Yeah. If you toss a head, your number of heads before the first tail has to be at least 1, whereas the random variable x could perfectly well be 0. It will be 0 with probability q. So we've got the probability of a head, and I guess I might as well substitute in the value p for that. Okay, the expectation of x given h. Well, we've got one head already in the bank, right? And then on top of that, we have the expected number of heads when we flip a coin, the expected number of heads before the first tail, which we just worked out to be p over q. So this is the one head we know we have because we're conditioning on the first toss being a head. And this is the number of heads that we expect to follow that, which will be p over q. Here, the probability of getting a tail is q, and this expectation is 1, because if we toss a tail to start with, there has to be at least one tail before the first head, and then we'll get q over p to follow that. And this looks like a mess, but it simplifies incredibly. This is equal to p plus p squared over q. I found a great way to do this. Sorry. This business of doing algebra with p's and q's is a real art, because q is, of course, 1 minus p, and there are many different ways of writing things. And the clever way I found after dinner tonight was to write this as q plus p over q, and to write this as p plus q over p, which makes it obvious that this sums to p over q plus q over p. And now that I've worked this out very formally by conditional probability, I have to be honest with you and say, and this is obviously correct, because what can happen? Well, there are two possibilities. Either you start out by flipping a head with probability p, and you'll get a geometric distribution of heads terminated by a tail. That has an expectation of 1 over q. Or you will start out with a tail and get a geometric distribution that's terminated by a head. That has an expectation of 1 over p. This quantity p over q plus q over p is greater than 2, unless it's equal only if P equals 1/2. Okay, let's think about the second run. The second run is actually much easier. So for the second run, we want to calculate the expectation of R2, and that is, of course, the probability that we start with a head times the expectation. Now, if we start with a head, the second run consists of what side of the coin? Tails. So this is now the expected number of tails before we get a head. So this will be the expectation of y plus the probability that we start out with a tail times the expected length of a run of heads. Okay, the probability of getting a head is P. The expected length of a run of tails is 1 over P. The probability of starting with a tail is Q. The expected length of your second run of heads is 1 over Q. This gives you 1 plus 1, which is 2. So this is really quite an interesting result. You take an unfair coin, toss it over and over and over again. The expected length of the second run and of all the even-numbered runs is precisely 2. But the expected length of the odd-numbered runs is greater than 2. And if you want to see why it's much greater, you can say, well, let's consider the case where the coin comes up heads 99% of the time. The overwhelming majority of times you will start with a head and get an enormous number of heads before it's finally terminated with a tail. Every once in a while, you will start out with a tail, and that run of tails will almost certainly have a length just 1 because the second toss is virtually certain to be a head. But you'll get so many more cases where you have a long run of heads than a short run of tails that the average will be much greater than 2. And then when you get to the second run, that phenomenon doesn't occur because if you started out with a head, which will happen most of the time, you will typically get only 1 tail on the second run. If you started out with a tail, which is rather an unlikely event, you will get an enormous second run of heads, and when you average it all out, it comes out to 2. Yeah, Katie?
Are you missing a complement on one of those H's?
Yes, thank you. Thank you. Thank you. Okay.
Whoa.
Or is it the other one?
That
The y given tails? Is it the expected value of y given tails?
Okay, let's see.
Is that where you need it?
Yeah, you should have a y in both terms, not a y and an x, right?
Yes, thank you. I had 2 mistakes. Okay.
Oh.
No, wait a minute.
The x was right.
Sorry, let me step back and think. Okay. The second run will consist of tails if we started out with a head, and it will be a run of heads if we started out with a tail. So this correction was correct, but otherwise it's right. Okay, with the Harvard-Yale game coming up, I'm going to do one last example. This is topic number 10, called 2 wins take all. And this is one where I was unable to figure out an alternative method for getting the formula for conditional expectation by writing down an infinite series, although it's a fairly simple sounding problem. So here's the scenario. One Harvard-Yale game isn't Harvard and Yale agree they're going to keep playing football games every day against one another until finally one team wins 2 games in a row, and then the series is over. And there are 2 interesting questions you can ask about this. One is, if Harvard wins an individual game with probability P, first, what's the probability that Harvard will win the series? That is, that Harvard will win the game, will win 2 games in a row before Yale wins 2 games in a row.
Sorry, your battery died.
Oh.
That's right.
Thank you.
Sorry.
And then the more interesting question is, what's the expected number of games in this series? And that's really, you may be pretty good at these Achilles versus Hector duel problems now, but that's a hard one to work out by other techniques. So Harvard wins a game with probability P, and while I'm not going to write it on the board because I need lots of space to do the calculation, the series ends the minute a team wins 2 consecutive games. So let's define some events here. H1 and H2 mean Harvard wins game 1 or 2 respectively. Y1 and Y2 mean the same thing for Yale. Capital H will denote the event that Harvard wins the series. That is, Harvard wins 2 games before Yale wins 2 games. And Y is the event that Yale wins the series. Okay, this is sort of a preliminary calculation because it doesn't involve expectation, but it will show you the general technique in a context with which you're already familiar. So this is a preliminary. Preliminary. We're going to compute the probability that Harvard wins the series. And I will say right off the bat, I think most of you already know and may already have spotted a technique for doing this. You can say, oh yeah, I can figure this out. There are 2 cases. Harvard wins the first game, and then we have a whole bunch of Yale followed by Harvard. And finally, after one of those, Yale followed by Harvard, Harvard wins the next game. And the probability that this will happen is P for this, and the sum of a geometric series for all these possibilities. And since the probability of Yale wins and then Harvard wins is QP, I'd expect to see a 1 minus PQ in the denominator, and you will. So this one can be done by infinite series, though you also have to consider the other possibility. You can have lots of YHs, and then after lots of indecisive pairs of games, Harvard runs off 2 wins in a row. And you say, again, this is the sum of an infinite series because we can have any number from 0 on up of Yale, Harvard wins like this, followed by P squared for 2 Harvards. So this can be done by techniques with which you're already familiar, but you still have to split it up. You still have to split it up into 2 cases. You say it's different depending on whether Harvard wins the first game or whether Yale wins the first game. Okay, here goes. This is doing it without ever talking about an infinite series, and the trick is not entirely obvious. Namely, you have to condition on the second game. So we want to calculate the probability that having won the first game, Harvard wins the entire series. And we can say, well, it all depends on the second game. If Harvard wins the second game, the series is over. If Yale wins the second game, then the series continues just as if Yale had won the first game. So I can write it down like this. This is the probability that Harvard wins the second game times the probability that Harvard wins the series given that it won the first two games. This is 1, but I won't substitute that in yet. And then I have to add on to that the probability that Yale wins the second game multiplied by the probability that Harvard wins the series given that they won the first game but then lost the second game to Yale. Everyone comfortable with this so far? This is the idea of you split the sample space into disjoint events, just two of them here, either Harvard wins or Yale wins, and you do the probability calculation in the two separate cases and add them up. So let's put some numbers into this. The probability that Harvard wins the second game, or any game for that matter, is P. The probability that Harvard wins the series if it wins the first, conditioned on its winning the first two games, is 1. The probability that Yale wins the second game is Q. Okay, the probability that Harvard will win the series if it won the first game and Yale won the second game can be expressed as 1 minus the probability that Yale wins the series if it has already won the first game or any other game for that matter. That is, you have to say, in this situation, Yale has already got one game in the bank, and the probability that Harvard will nonetheless win the series is 1 minus the probability that Yale will win the series after it's already won the first game. Everyone comfortable with this so far?
I thought we already knew Harvard won the first game.
Pardon?
Didn't we already know Harvard won the first game?
We're conditioning on Harvard winning the first game, but if Yale wins the second game, apart from the fact the series would have ended if Yale had won the first game too. What goes on in the rest of the series depends only on who has won the most recent game, because 2 wins ends the series. Okay, now I can interchange Harvard and Yale if I interchange P and Q, right? So without going through the full analysis, I can write down that the probability that Yale will win the series if they won the first game is Q times 1 plus P times 1 minus the probability that Harvard will win the series if it wins the first game. Exactly the same reasoning, but applied to Yale rather than Harvard. We're conditioning on the second game. If Yale wins it, they win the series. If they don't win it, we go back to the situation where Harvard has the 1 game advantage. Yes?
I'm actually so confused about what Sue brought up.
About what?
Going from the last term in the first line to the last term in the second line.
Going from here to here? From here to there? Okay, so here we're asking, what's the probability that Harvard will win the series if they won the first game but Yale won the second game? Okay. So think about this. You pick up your newspaper and you read only Yale won the most recent game in this never-ending series. And you ask yourself, what's the probability that nonetheless Harvard will win the series? And your answer has to be, it's 1 minus the probability that Yale will finish off winning the series having already won the most recent game. And what's a little bit tricky about this, Anna, is that I've got a y2 here, and I write a y1 here, because this doesn't depend on whether it's y1, y2, or anything else. This is just the probability that Yale will win the series starting from a situation where they already have the most recent win. Okay? Now, though the notation is strange, I've got two equations and two unknowns, don't I? I have the probability of H conditioned on H1 and the probability of Y conditioned on Y1 related to one another, and I can substitute one of these equations into the other, and I think I will choose to eliminate Yale. So what I'm going to do is substitute this equation into that one. And this is a standard way of dealing with this sort of problem. You get a bunch of equations by using conditional probabilities, and then you use ordinary algebraic techniques to solve them. So I can say the probability that Harvard will win, conditioned on their already having won the first game, is P plus Q times 1 minus this thing, which I've got down here. That is Q plus P times 1 minus the probability that Harvard will win, having already won the first game. Have I got enough parentheses? No. No, that's all. 3, 3. Okay. 4? 1, 2, 3. Yeah? Wow. Okay. So now I have an algebraic equation that I can solve for this quantity. Let's do this. Probability of H given H1 times 1 from here minus, and what's the coefficient over here? The coefficient on the other side is Q times P, and over here we've got 1, 2 minus signs. I bring it to the other side. I've still got a minus sign. So it's 1 minus PQ. Okay, what are my other terms? Well, I got a P there. I got a Q there. I'm always happy with P plus Q because that's just 1. I've got a minus Q there. I've got a P there. And is that? That doesn't look right. Oh, yuck. This Q times 1 minus in the printed notes I said the rest is all just algebra, so I've got to get this right for you. Let's see.
Squared. It's P plus Q minus Q squared minus PQ.
P, thank you.
I think I got all the money.
It's that, isn't it? Yes. Okay. It's Q times Q plus P. And now that's P plus Q minus Q, which is just P. Thank you, Katie. I knew what the right answer was, but I wasn't getting it. So the probability that Harvard will win after winning, conditioned on winning the first game, is P over 1 minus PQ. And I have to say, this is arguably obvious on the grounds, okay, Harvard has already won the first game. you can have any number of these YHs. That's a geometric series with a factor of PQ, and then a factor of P for Harvard winning the final game. So when you add all these up, which you can now do in your head, having done so many of these problems, you get P divided by 1 minus PQ. Nonetheless, I've done this without ever writing down or summing a series. And now I'm running low on space, so I'll write the other result up here. The probability that Yale will win, having won the first game, is obtained just by interchanging P and Q everywhere. So that's Q over 1 minus PQ on the basis of an identical calculation. And now I can finally go back and compute the whole answer. And I'm going to do that up here so that everyone can see it. So my final answer is the probability that Harvard wins the series is the probability that Harvard wins the first game times the probability that it will win the series conditioned on that, plus the probability that Yale wins the first game multiplied by the probability that, conditioned on that unfortunate event, Harvard nonetheless wins the series. And this gives me P times P over 1 minus PQ. This is the conditional probability I just calculated. This is the probability that Harvard wins the first game. And then I have to add on Q. Now, I never calculated the probability that Harvard would win the series if Yale won the first game, but I did calculate the probability that Yale would win the series if it won the first game. So I'll calculate this probability by taking 1 minus this thing, 1 minus Q over 1 minus PQ. And when you do all the algebra, you get putting everything over a common denominator of 1 minus PQ. Let's see if I can do this. We've got a P squared from here. We've got from here a Q minus PQ squared. And we've got from here a Q squared. I found a simpler way to do this, and I can't reconstruct how I did it. I know I've got the right answer, and again, I can't get it. Okay, P squared over 1 minus PQ. Plus Q minus PQ squared over 1 minus PQ minus Q squared over 1 minus PQ. What is it?
You can factor P squared minus Q squared. It's P plus Q times P minus Q, which is P minus Q.
Oh, very nice. Okay. Let's see if that will bail me out. So we'll combine these two. That's P plus Q times P minus Q. That's P minus Q. And what I have left here is a...
No, it's not the same as the answer you gave. Yes, it is. The Q's cancel.
Oh, yeah. And then I've got, thank you, Jerry. And then I've got this Q, and I've got minus PQ squared,
Which is P squared.
where I don't like the sign on that. Have I?
P minus PQ. I think you're all right. P minus PQ.
That must be equal to what I've got, which is P squared times 1 plus Q over 1 minus PQ.
Actually, I just get P squared.
You got a Q squared up there.
Yeah, you can factor again. You can factor 1 minus q squared. Oh, yeah, 1 minus q squared in the original term. So p times 1 minus q squared. So that's p times 1 minus q times 1 plus q. And the 1 minus q goes to p, so you get p squared times 1 plus q.
Right.
I'd be happy just to leave you. We want to run that by me again?
The second equation should be p times 1 minus q squared.
That's right here?
Nope, the next one.
The next one.
Yep, should be. Then you can make that, you can simplify that.
Yes.
P minus.
Okay, so this is P times 1 minus Q
Square.
times 1 plus Q,
Yeah.
where I factored that, which is, thank you, Catherine, P squared times 1 plus Q over 1 minus PQ. Great. Okay, so we've got the right answer in this case. Now, that was just a lead-in to the very slightly more complicated problem of getting the expected length of the series. So this is my last calculation for tonight. And I've got 10 or 15 minutes, do I? Okay, so now we're going to compute E of x. The expected length of the series, and I'm going to show you that it's 2 plus PQ over 1 minus PQ, although I haven't been able to see any way of looking at this problem that makes that formula obvious. So here goes. First, let's ask, using the same sort of technique, what's the expected length of the series given that Harvard has won the first game? And again, we'll condition on the second game. That's the probability that Harvard wins the second game times the expected length of the series given that Harvard wins the first two games. Has somebody spotted the numeric value of this term? 2, because the series is over. Harvard won the first two games. And then we have to add on to this the probability that Yale wins the second game times the expectation of the length of the series given that Harvard won the first game and Yale won the second game. It's got to be at least 3 games long now, because the first thing that could possibly end it is Yale winning the third game. Okay, let's put some numbers in here. This is little p. This, as has already been pointed out, is 2. What's the probability that Yale wins game number 2? Q. And now the expected length of the series, given that Harvard won the first game and Yale won the second game, is fairly easy. Maybe nobody noticed that Harvard won the first game. The folks down in New Haven are just saying, Yale has just won a game. How long is this series going to go? So we will add on 1 for the game that Harvard won before everything got really started in the minds of the Yaleys, and then say, on top of that 1, we will have the expected length of a series that starts out with a Yale victory. Does everyone see this is the same sort of argument as before? We add on 1 for the game that Harvard won, and then we say, since Yale won, that's in a sense a fresh start to the series. Okay? The expected length of the series, if Yale wins the first game, instead of a P here, I have a Q. Because the probability that Yale wins a game is Q. So we'll get Q times the length of 2 for the series if that happens, plus P here times 1 plus the expected length of the series if Harvard wins the first game. All I've done is to interchange Yale and Harvard everywhere in the previous formula while interchanging P and Q also. Okay, now we can go ahead and solve this for the expectation of the length of the series given that Harvard has won the first game. That's 2p. Let's see if I can do the algebra this time. Plus q times 1 plus the expected length of one of these series given that Yale has just won the first game. So that's 1 plus 2q plus p times 1 plus the expected length of the series given that Harvard has won the first game, followed by a lot of closing parentheses. So now I've got a formula for the expectation of the length of the series given that Harvard has won the first game. Let's collect all the terms that involve that over here on the left. We've got a coefficient of 1 here, and we have a coefficient of q times p over here. 1 minus pq. Now let's see if I can correctly collect all the terms that are on the left. We've got 2p, which is p plus q. So I've taken those into account, and I've taken the 1 into account, plus 2q squared. Is that the way I want to write it? No. Plus q, writing this q, times q plus p. And that's everything, because I already took this term over to the other side. And the reason I did that crazy business of splitting up 2p into p plus p is that's 1 and that's 1. And this is 1 also. So this is 2. Is it really 2? Yes. It is 2 from here plus
p plus 1 plus q squared plus q.
It can't be 2
Two.
because 1 is multiplied by
There is
q.
actually just a q, because you haven't multiplied it by the q.
p plus 1 q squared plus
I've got
q squared plus
Q
p.
times q plus p.
And that q plus p that you underlined that you thought was 1 is multiplied by a q, so it's not,
Yeah.
you can't add it to the,
Yeah, you need to multiply in the q first.
Back up, if you go 2p plus
The
1
one in the
minus
parentheses,
p.
q plus p.
I'm sorry. I see. So I've got p plus q times this whole mess. Sorry. So this is
Plus 1
P plus 1 plus
Q
Q
Q
plus
squared
Q
plus
times Q plus 1, which is P plus 1 plus Q squared plus Q, which is 2 plus Q squared, which I happen to know is the right answer. So the expected length of the series, if Harvard wins the first game, is 2 plus Q squared over 1 minus PQ. It certainly is nice to have a live audience. People watching on video are no help with the algebra. Okay, so
You got, the notes say it should be 2 plus PQ, not 2 plus Q squared.
um,
And that's what I got.
Yeah, you miswrote. The last term in the second last equation should be Q, and you wrote a P instead.
2 plus q squared.
If I can,
sure, provided you signed a waiver.
and when it expands out, that guy and that guy give you the 2, and that guy's left over from that term.
Wait a minute.
I got just what you did. I got 2 plus q squared.
Yeah,
I
you've
think
got the right final answer. The 2 plus Q squared is right at this point. And, okay, now the corresponding equation for the length of the series, if Yale wins the first game, has to be 2 plus P squared over 1 minus PQ, because if I did the same calculation interchanging Harvard and Yale, I just interchange all my P's and Q's. So now I have managed to work out the expected length of the series if Harvard wins the first game, and the expected length of the series if Yale wins the first game. And without writing on the bottom of the board, I can now finish the calculation off by getting the expected length of the whole series. The expected length of the series is the probability that Harvard wins the first game times the expected length of the series if that happens, plus the probability that Yale wins the first game times the expected length of the series given that Yale wins the first game. Okay. You got the general message now about using conditional expectation. You split things up into cases, tackle them individually, and then put them all together at the end. And this is an incredibly messy calculation, but I think I can do the algebra on this one. So the expectation of x is P for Harvard winning the first game times 2 plus Q squared over 1 minus PQ. As I recall, none of this algebra is done out in the book. He just gives the answer. Plus Q for here times 2 plus P squared over 1 minus PQ. And now I have to figure out how to combine these. And the way I figured out how to combine them was I've got 2P, that uses that, plus 2Q, that uses that, plus PQ squared plus QP squared over 1 minus PQ. 2P plus 2Q is Q, and this factors into PQ times P plus Q, so it's 2 plus PQ over 1 minus PQ, and that I know is the right answer. We can do one check on this just to finish up in a very special case. If both P and Q are 1/2, so the teams are evenly matched, then this formula says the expected length of the series is 2 plus 1/4 divided by 1 minus 1/4, which is 9/4 over 3/4, which is 3 games. And I know that's right, because you figure some team has to win the first game. After that team has won the first game, you start a geometric series, and the geometric series ends if the winner of each game is the same as the winner of the preceding game, which happens with the probability of 1/2. So you have a geometric series that ends with the probability of 1/2, and we already know the expected length of such a series is 2. So we can say in this very special case, there's 1 game to start the series, and then there's an expected 2 games before we end up with a game that repeats the winner of the preceding game. Yeah, Catherine?
Is that in the second term there, should that be 1 minus PQ instead of 1 minus P squared? Oh, wait.
No.
Why is it 1 minus P
Which one?
The denominator of the second term.
Oh, yes, thank you. That's not an algebraic mistake. That's just a typo. And I tried to find another way of doing this. I'll show you what I tried, but I didn't come up with an answer. You can say there are basically 2 ways this series can go. That is, if Harvard wins the first game, you have a Harvard win followed by a lot of Yale wins, then Harvard's, followed finally by another Harvard win. Or you have lots and lots of Yale wins followed by Harvard wins, and finally Harvard wins another game. But I could not, with about 15 minutes of effort, tease this formula out of this analysis. And the book's claim about this problem is that doing it straightforwardly by summing series is extremely difficult. So I think that I shouldn't be entirely surprised that I couldn't find an easy way to do it. So this is a bit messy, but the mess is all in the algebra with the P's and Q's. The basic approach is fairly simple. So next week after the quiz, I'm going to do a couple more interesting problems in this style, and then we will switch over to studying random walks, where this technique is going to become our standard. That is, we'll take things that look infinite and turn them into equations, which turn out actually to be quite easy to solve.